Every night, after the fryers cool down in thousands of restaurants, something happens that almost nobody thinks about. Thick, dark, spent cooking oil gets poured into a bin out back. Oil that fried a day's worth of fries, chicken, and everything in between. To the kitchen staff, it's just grease, a mess to deal with. But that same greasy, unwanted liquid is about to become fuel for an actual vehicle engine. And the journey it takes to get there is stranger and more chemically fascinating than most people would ever guess. If figuring out how everyday waste turns into something genuinely useful is your kind of rabbit hole, hit subscribe now, because this transformation involves a chemical reaction that essentially rebuilds the oil molecule from the inside out. Collection is where it all starts, and it's a bigger logistical operation than you'd expect. Specialized trucks run routes to restaurants, fast food chains, and commercial kitchens, pumping used oil out of collection bins and into sealed tanker compartments. This oil isn't uniform, it's a mixture of different fry oils, contaminated with food particles, breadcrumbs, batter bits, water from cooking, and sometimes salt and seasoning residue. Before this can become anything close to fuel, all of that has to go. This logistical phase highlights a fascinating economic shift. Used cooking oil has become so valuable that it has spawned its own black market. Often referred to as yellow grease in the trade, this discarded liquid is no longer treated as waste, but as a prized commodity. In many major cities, organized theft rings target the storage bins behind restaurants, siphoning out thousands of gallons of grease overnight to resell to illicit processors. Because of this, modern collection companies now deploy heavy-duty steel containment bins equipped with digital smart locks, GPS tracking sensors, and integrated level monitoring systems. These high-tech bins notify the dispatch center exactly when they are full, optimizing truck routes and preventing overflow. What used to be a smelly chore for kitchen staff has turned into a high-security asset protection operation, proving just how desperately the energy sector wants this raw, greasy material before it even reaches a processing facility. At the processing facility, the oil is pumped into large holding tanks and run through an initial filtration stage. Coarse mesh filters catch the big stuff first, chunks of food debris, burnt particles, anything solid. Then it moves through progressively finer filtration, sometimes involving multiple filter presses, stripping out smaller sediment until the oil starts looking cleaner, though it's still far from usable. Next comes heating. The oil gets warmed in large tanks, sometimes to around 50 or 60 degrees Celsius, which does two important things. It lowers the oil's viscosity, making it flow easier, and making any remaining impurities easier to separate out. And it helps water content rise and separate from the oil itself. Water is a genuine enemy in this process. Even small amounts of residual water can interfere with the core chemical reaction that turns this oil into fuel. So operators run the heated oil through centrifuges, spinning it at high speed to fling out water droplets and any remaining fine sediment based on density differences. What comes out is significantly cleaner, drier, filtered cooking oil, ready for the chemistry stage. This is where biodiesel production actually earns its name, through a reaction called transesterification. Sounds complicated, but the concept is straightforward once you break it down. Used cooking oil is made up of triglycerides, molecules built from a glycerol backbone with 3 long fatty acid chains attached. Those fatty acid chains are actually what we want, because once separated and chemically modified, they behave remarkably similarly to diesel fuel. The glycerol backbone, on the other hand, is not something we want in the fuel at all. To pull this apart, the filtered oil gets mixed with methanol and a catalyst, typically sodium hydroxide or potassium hydroxide, inside large sealed reactor vessels. The mixture is agitated and heated to a controlled temperature, usually somewhere around 50 to 60 degrees Celsius, and held there for an extended reaction period, often an hour or more depending on the batch and the specific process design. During this time, the catalyst facilitates a reaction where the methanol molecules essentially swap places with the glycerol backbone. Each fatty acid chain breaks free from the glycerol and bonds instead with a methanol molecule, forming what's called a fatty acid methyl ester. Multiply that reaction across billions of molecules simultaneously, and by the end of the reaction period, you're left with 2 very distinct products floating in the same tank. This chemical transformation requires incredibly precise real-time calibration because a major danger lurks in the reactor, saponification or the accidental creation of soap. If there's even a fraction of a percent of water present in the incoming oil, or if the free fatty acid levels are too high, the sodium hydroxide catalyst will react with the water and fat to make actual soap instead of biodiesel. This unwanted side reaction turns the entire batch into a thick, useless gel that can ruin industrial equipment and halt production for days. To prevent this, technicians run rapid chemical titrations on every incoming batch of oil to determine the exact amount of catalyst and methanol needed to neutralize the free fatty acids before the main reaction begins. It is a delicate chemical tightrope, where a tiny fluctuation in temperature or moisture can ruin thousands of gallons of potential fuel. Separating these two is actually one of the more visually satisfying parts of the whole operation. The reacted mixture is pumped into settling tanks and left to rest, sometimes for many hours, allowing gravity to do the work. Because glycerin is notably denser than the methyl esters, it sinks and forms a distinct lower layer, while the biodiesel floats on top. Once separation is complete, the glycerin layer is drained off from the bottom, leaving raw biodiesel behind. This glycerin byproduct isn't wasted either. Once refined further, it becomes an ingredient used in soap making, cosmetics, and various industrial applications, a secondary supply chain born entirely from this fuel-making process. The raw biodiesel that remains still isn't ready for a fuel tank. It carries residual methanol, leftover catalyst, small traces of soap formed as a side reaction, and trace glycerin that didn't fully separate. This is where washing comes in. The biodiesel is gently mixed with warm water, sometimes in multiple wash cycles, allowing the water to bond with and pull away these water-soluble impurities while leaving the fuel itself untouched. Each wash cycle is followed by another settling period, letting the water, now carrying the impurities, separate back out and drain away. After washing, the biodiesel is still slightly cloudy and often carries residual moisture from the washing stage itself. Drying comes next, using vacuum drying systems or gentle heating under reduced pressure to evaporate any remaining water without degrading the fuel through excess heat exposure. What emerges from this stage is a clear, golden liquid, remarkably similar in appearance to fresh cooking oil, which is a strange thing to witness when you remember what this liquid looked like just days earlier: dark, cloudy, and full of food debris. Before any of this fuel gets shipped out, it goes through rigorous testing. Laboratories check for exact specifications: viscosity, cetane number, which measures how efficiently the fuel combusts, sulfur content, water content, and free fatty acid levels. These aren't arbitrary numbers. Engines running on biodiesel that don't meet exact specifications can suffer clogged filters, reduced performance, or long-term damage. So testing standards are strict, often governed by international fuel quality certifications that batches must pass before distribution. The finished biodiesel gets blended, sometimes used at full concentration, sometimes blended with conventional diesel at specific ratios depending on regional regulations and vehicle requirements, then shipped out to fueling stations and fleet operators who've committed to lowering their carbon footprint. What's easy to lose in all this chemistry is the sheer scale of what's being redirected. Restaurants worldwide generate enormous volumes of used cooking oil daily. Oil that historically got dumped, poured down drains causing serious sewage blockages, or simply discarded as unusable waste. Now it's quietly powering trucks, buses, and machinery, all because a repeatable chemical reaction figured out how to separate what we don't want from what we do. So think about your own kitchen or your favorite restaurant and the oil that gets thrown out after every fry session. How much fuel is quietly slipping through the cracks in your own city, uncollected and unused? Drop your thoughts in the comments, and if industrial transformations like this genuinely interest you, subscribe, because we've got more of these stories still to go.